investigate it. Let's get more data. I'm all in. But the moment you say, I don't know what I'm looking at, therefore I know what I'm looking at. I'm looking at aliens. That is a leap. Oh my gosh, that's a leap. And it's a leap I'm not prepared to take. What's gotten a lot of attention of late, deservedly, is we've had now 3 visitors from interstellar space. Love it. We've been looking for these puppies for decades, by the way.
So why doesn't "I don't know what this is" justify concluding "I know it's extraterrestrial technology"? Evidence is not the same as surprise. Evidence is a pattern in data that is more expected if one explanation is true than if it is not. A hypothesis is a specific claim about a cause and mechanism that makes testable predictions. We also carry priors, which are our starting expectations based on the rest of physics and past observations. The assumption we use here is simple: that the same physical laws apply to rocks, gas, and light, whether they come from Earth orbit or interstellar space. An unidentified observation is a lack of information, not a distinctive signature. Ordinary causes have many pathways to produce confusing data: instrument artifacts, selection biases, and rare but natural phenomena. So they remain more expected until we see a feature that ordinary causes rarely produce. In short, surprise by itself does not favor the extraordinary. Only a discriminating prediction does. How do our telescopes and surveys shape which interstellar objects we even notice? An interstellar object is a body on a path not bound to the sun. Its trajectory is hyperbolic, meaning it will not return. A selection effect is a bias introduced by the way we detect things, not by the things themselves. Our surveys find objects because they reflect sunlight or emit heat, and brightness falls rapidly with distance by the inverse square law. This means we mostly detect the largest, brightest, or nearest objects, and we miss the bulk of the population. We also preferentially catch objects that pass close to Earth and in observing geometries near opposition, where they are brighter, and our motion-finding pipelines are most efficient for moderate skyplane rates. Extremely fast, trailed movers or very slow ones are easier to miss. These constraints create oddities. An object seen at a high phase angle, the angle between the sun, object, and telescope, can show extreme brightness swings that look like an exotic shape even if it is modestly elongated. Timing matters too. If a discovery happens late in a flyby, we only get a short arc of data, which inflates uncertainties about speed and size. The net result is that early detections are drawn from the tail ends of distributions, where unusual-looking data are expected even for ordinary rocks. By what natural processes are solid bodies launched from one stellar system into interstellar space? Gravitational scattering is when a small body exchanges energy and momentum with a massive planet or star and gets flung onto a new trajectory. During planet formation, countless icy and rocky fragments interact with growing planets. A fraction receive energy kicks that exceed the system's escape speed, ejecting them into interstellar space. Simulations and observations of young systems indicate that giant planets and binary stars are especially efficient at this ejection. Over hundreds of millions of years, each planetary system can discard vast numbers of bodies. This predicts a steady background of interstellar visitors even if life never arises anywhere. Their speeds should align with typical stellar motions in our region of the galaxy, which is consistent with measured approach speeds. Interstellar travel also alters surfaces. Cosmic rays and micrometeoroid impacts darken and degas outer layers, which changes reflectivity and can mute comet-like activity. Natural ejection is not rare. It is the default endpoint for a significant fraction of planetesimals. What do we actually learn from a weird light curve or a slight departure from a purely gravitational path? A light curve is the change in brightness over time, which depends on an object's shape, spin, and reflectivity. Albedo is the fraction of light a surface reflects. A non-gravitational acceleration is a small push not explained by gravity alone, often from outgassing, the release of vapor as sunlight warms volatile ices. These inferences are tricky because different physical scenarios can produce similar light curves. A long, thin object and a more compact object with strong albedo patches can both yield large brightness swings as they spin. A small push away from the sun can result from outgassing, such as low levels of CO, CO2, or water vapor, or the release of molecular hydrogen trapped in ice that goes undetected when production rates are weak, dust is scarce, or observations miss the relevant wavelengths. Laboratory studies show that space weathering can build fragile, porous surfaces that release gas efficiently when warmed. Radiation pressure, the push from sunlight on a surface, can also matter if the object has an unusually high area-to-mass ratio, which is plausible for fluffy aggregates formed by gentle sticking of grains. This is theoretically suggested, not confirmed, but remains consistent with some data. Competing natural models make different secondary predictions, such as thermal emission patterns, rotation changes, or specific gas species. So, targeted follow-up is what narrows the options. The key point is that weird and sparse data often reflects degeneracy, not uniqueness. What would count as compelling evidence for technology rather than geology or ice physics? A technosignature is a pattern most naturally produced by the actions of a technological process and very unlikely under known non-living physics. Narrowband radio emission, a tone confined to a tiny frequency range with a Doppler drift that tracks the motion of a transmitter and repeats on schedule, is one example. Because thermal and natural plasmas produce broad, noisy spectra, not stable, tonally precise carriers. Optical or infrared signals with engineered timing, like pulses encoding a non-astrophysical pattern, or a modulation that matches a designed clock rather than a rotating or orbiting body, would be another. In reflected light, a surface spectrum showing sharp, periodic features consistent with manufactured structures, not known minerals, would be diagnostic. For moving objects, repeated, controlled trajectory changes that cannot be explained by venting gas, coupled with detectable signs of an active propulsion mechanism, such as waste heat consistent with power generation, exhaust plumes or directed energy, or radiation pressure sailing from a large reflective surface, would be decisive. A sustained acceleration with no exchange of momentum via expelled mass or photons would conflict with well-tested conservation laws. Crucially, these signatures must be recorded by multiple independent instruments and persist under re-observation to rule out instrument quirks and one-off noise. This is a high bar, but it is specific and achievable. So, why should we treat today's strange sky reports as prompts for better measurements rather than as declarations of aliens? Because comparing hypotheses requires both priors and likelihoods, natural ejection, selection effects, and data sparsity already explain why first discoveries look odd, while technology adds assumptions that we do not yet need. The way to move from ambiguity to knowledge is to collect data that discriminate. That means building wide-field surveys with fast cadence to catch objects earlier, equipping them with spectroscopy to detect faint gases, and coordinating radar and thermal follow-up to break the degeneracies of light curves. It means prepositioning rapid response spacecraft able to intercept a future interstellar visitor so we can measure mass, composition, and activity directly rather than inferring them from a distant sparkle. It also means publish in open, calibrated data with error bars large enough to be honest, because transparency lets others test alternative explanations. Skepticism here is not rejection. It is the method that protects us from self-deception while keeping us aimed at the real prize. If a technological signature appears, these same disciplined tools will reveal it unambiguously. Until then, the responsible answer to, "I don't know what this is," "Let's learn more," and then we do the work that makes extraordinary evidence possible. Like if this was interesting and hit the subscribe for more.